Thanks, Stefan. Thanks to all of you survivors for coming back after the 5 hours of yesterday. So today I'm going to tell you about bandit linear optimization and also combinatorial optimization. So we'll do online combinatorial optimization. And bandit linear optimization. Okay, so this will be the topic for this morning, and we'll go through a few fun topics, including interpoint methods and the entropic barrier. But first, let me just remind you a key theorem from yesterday on Mero Descent, which you should have in mind, during the entire lecture. Okay, so reminder on Mero Descent. Okay, so here is the key theorem. I'm just going to state it as a completely deterministic thing. So for any L1 up to LT vectors in Rn, okay, I fix my convex function, right? Fix phi convex, which is my mirror map. So for any sequence of losses in Rn, if I do the following equation, xt plus 1 is equal to the arc mean over x in k of the Bragman divergence between x and grad phi star of grad phi of xt minus eta lt. Okay, so this was my Mero Descent. You remember, you map to the dual, you take a gradient step, you map back to the primal, and you project on your set of constraints. Right, I have fixed k is a convex body and phi is a convex function on a superset of k. Then we have the following inequality. If we have the following, so if for any yt such that the grad phi of yt is in the segment grad phi of xt, grad phi of xt minus eta lt. Okay, so what does it mean? This is a segment in the dual. So take any point in the primal whose image in the dual is in that segment. What we wanted was that that phi was well conditioned on this set. One has the Hessian of phi at yt is bigger than c times the Hessian of phi at xt. Then, okay, so if we have this, then we have the following regret bound. The sum of lt dot xt minus y for any y is upper bounded by the Bragman divergence between y and x1 over eta plus 2 eta over c, the sum for t equals 1 to capital T of the local norms of LT, dual local norm, okay, squared. Okay, so I hope you remember this notation of the dual local norm. Yeah, so this was the star theorem from yesterday afternoon, which we're going to use again and again. Okay, so this is really the main statement. And also recall, so let's call this star. Okay, also recall that for phi of x, which is the sum of xi log xi, okay, well conditioning is true with c equals 1 for non-negative losses. Okay, so if you do Mero Descent with the entropy, or if you do multiplicative weights in the special case when k is a simplex, you don't need to worry about this well conditioning condition. It's just automatically verified. Okay, you remember, I hope you remember this. Okay, I think that's all I want to say for the reminder. And now we can move to the topics of this chapter. So let's start with online combinatorial optimization. So in a sense, this paragraph is an application of what we did yesterday, but an important one. Okay. So in online combinatorial optimization, what we're going to play with, our action set, is going to be a subset of the hypercube. So action set is A, a subset of 0, 1 to the n. Okay, so what am I thinking? What I'm thinking when I write this is that I think that I have a graph with n edges, and this represents, valid subset of edges. So for instance, this could represent ST paths in my graph. I fix some source node and some target node, and I look at all the ST paths. Or maybe I look at all the spanning trees in my graph, or any combinatorial structure. Okay, so this is a very, very general thing, and it encompasses any type of combinatorial optimization in some sense. And to simplify, I'm also going to assume, so I'm going to talk about element of this set as concept. Okay, so we say that little a in A is a concept. Okay, and this is a and script A is a concept class. Okay? And to simplify, I'm going to assume that the size of the concept are all the same. This is not absolutely necessary, but it will make the calculation easier. So we assume that the L1 norm of A is equal to M for any A in A. Okay, so again, an example just to make sure that we are all on the same page. An example would be this. I have a graph like this. And maybe I have a source node here and a target node here. So this is T, this is S. And what I want to consider is any increasing path from S to T. Okay, so like this. Something like that. Okay, so my concept are increasing paths from S to T. And you can see, so, my vector, it just represents a value on every edge. And a vector with 0, 1 value, it just tells me whether I take an edge or not. And the allowed way to take edges is just so that it forms an ST path. Is that clear? Yeah? Okay, good. So now we're going to play our online learning game on this type of action set. Okay, so at every T, in capital T, the player picks AT in script A, and the adversary picks LT in 0, 1 to the n. Okay, so the adversary can put a unit loss on every edge in this graph. Notice that this is a different normalization from what we were doing yesterday, because yesterday we were assuming that the total loss was at most a unit, but now it's the loss per edge, which is a unit, which makes a difference. So, in particular, we have that AT.LT is, absolute value, let's say, is smaller than M. Okay, so the loss suffered can be at most M, and it's also non-negative.
So like a 0, 1 interval or the 0, 1?
Yeah, this is a 0, 1 interval, yes, yes. In fact, you can make a reduction between the 0, 1 interval or just value 0 or 1.
So one loss per
edge. Okay. Yeah, I think that I have n edges, right, in this problem. Okay, so let's see what kind of guarantees we can get for this problem. So the first naive attempt, or maybe first attempt for an algorithm. Let's say if you didn't know about Mero Descent, or in any case it makes sense to first try this. Let's just do multiplicative weights on this big set of actions. Okay? So multiplicative weights on A. So I can do that, right? Now what is going to be the regret guarantee? The regret is going to be, so the regret of this. Okay, we get square root t log of the size of the action set. That's what we had yesterday. But now notice that this was for unit loss, okay, per action. But now the loss can be m. So you get an m in front. Okay. And of course, the size of the action set, right? It's n choose m at most. It's bounded by n choose m. Okay. So the log of this is bounded by m log n over m. Okay, so this is bounded by m to the 3/2 square root t, and let me ignore right now logs. Okay, just to make, so this squiggly inequality now means that I also ignore log factors. So we get m to the 3/2 square root t. And what I'm going to show to you next is that this is suboptimal. You can do better than this. You can really exploit the geometry here more efficiently, and you can get m square root t. But to exploit the geometry, you have to, here, multiplicative weights did not realize at all that there is some information sharing between actions. Okay, they were all just completely independent things. And so in the hedging procedure, multiplicative weights did not realize that you can hedge, there is a related way to hedge on these different concepts. But Mero Descent will do that for you. So here, Mero Descent with the entropy on the convex side of the action set is not the same thing as multiplicative weights. So yesterday we said that if you do Mero Descent on a simplex, it's the same thing as multiplicative weights on the vertices. But if you do multiplicative weights on some other sets, it's not the same thing as Mero Descent with the entropy on the convex hull of those points. Okay? And we'll see this difference because Mero Descent will get a better bound. Should I remind you how we got this, or is everybody clear on this? I don't see. What? Okay. Okay, so just how do you get this? Okay, so you get this using this bound. So again, you remember that multiplicative weights is Mero Descent with the entropy, so we can use this remark, so we don't have to worry about this, meaning that this bound is just true. So what does it mean? So reminder. Let me introduce a notation just to clarify what we're doing. So let me denote LT Chech like this of an action A is just going to be the inner product LT.A. Okay, why am I doing this? Because now L Chech is really defined on the action set. Okay, it's a little bit simpler. So what do we have? We have that the regret of multiplicative weights on A with losses L Chech T from A to 0m. What is this? So we get two terms. We get a term which is the entropy term. Okay, remember it's this term. So this entropy term is just log of the size of the number of actions, which is A, over eta. Okay, this term. And now we have the local norms. Remember that for the entropy, the local norms are nothing but weighted Euclidean. I mean, they are always weighted Euclidean norm, but here just weighted Euclidean norm in the canonical basis. And the weights are exactly given by the probability of each action. So this is smaller than plus, let's say, 2 eta, the sum for t equals 1 to capital T. And what we have is that these norms are nothing but the inner product between pt and L Chech T squared. Okay, so pt, again, pt of A is the output of multiplicative weights. Okay, so remember the way it's updated, pt plus 1 of A is proportional to pt of A times exponential minus eta L Chech T of A. Okay, this was the formula for multiplicative weights. And again, this is just the local norm with the entropy. Okay, because the Hessian inverse of the entropy is exactly a diagonal where at a point x you have the entries x. So this is just the sum of PTA LHTA squared. Okay, so it's a weighted Euclidean norm. So now you know that this term, in particular, you know each entry is smaller than m squared. Okay, for each action, the loss is smaller than m, so the square is smaller than m squared. So this is smaller than m squared. Okay, so you get log of the size of A over eta plus 2 eta t m squared. So when you optimize, you get what I wrote here. Okay, so this was just a reminder of what we did yesterday. Now let's see what happens if you take, if you do Mero descent on the convex hull. Okay, so here when you did multiplicative weights on A, you would get immediately a distribution over the vertices. And from this distribution, you play at random. Now what does it mean to do Mero descent on this set? Okay, so second attempt. Let's do Mero descent on the convex hull of A with the entropy, with phi of x equals the sum of xi log xi. So what does this mean? So it means that at time t, the output is x sub t in the convex hull of A. What does it mean that it's in the convex hull of A? It means that there is a way to decompose this, you know, as a distribution over the vertices, okay? Which means this is equivalent to saying that xt is equal to a sum of, let's say, mu t of A times A, for A in script A, where mu t is a distribution. Okay, this is a definition of the convex hull. It's all the convex combination of the vertices. So now, when I see that Mero descent is telling me play this point xt, right? The picture is like this. So Mero descent is telling me play this point. What I'm going to do is that I'm going to decompose this point as a convex combination of vertices. So you know, in this case, for instance, it's with priority a half, I'm going to play this, and with priority a half, I'm going to play that. Now, of course, there is the algorithmic question of, given x, how do you find mu? Okay, and then there are, you know, we could do essentially a course on this, so we won't do it. And yeah, but there are many, many examples where you can do it. There are examples where it's hard to do it. It's not an obvious problem at all. Okay, but now given mu t, what you do is play at random from mu t. So the algorithm is obtain xt from Mero descent, find mu t, and play from it. Okay? Of course, the point is that if you play from mu t, in expectation, it's like playing from xt. Okay? So in particular, so the expectation when you draw A from mu t of Lt dot A, okay, which is your loss when you play A at random, this is equal by definition to Lt dot xt. So the regret of this algorithm is just exactly the regret of just Mero descent on the convex hull. Okay, is that clear? So now, yes, please.
So any convex combination is okay for this?
Any convex combination is okay. You just need to find one. Any is okay. But very soon, we're going to move to we're going to talk about the bandit version of this problem, and then the convex combination will matter. But right now, it doesn't matter. Yeah. Yes?
Just to be clear, like the difference between the exponential weights, like in this case, like the simplex, it's not the simplex of dimension A.
Exactly, exactly, yes. So here, multiplicative weights is you're doing it on the simplex delta of, of A. And what you're doing, so Mero descent on this with the entropy is not the same thing as Mero descent on the convex hull of A. That's exactly what's happening. Essentially, here, you see, here you have lost, like the geometry, you have lost the fact that you were, these points came from n space. They were in dimension n. Here you remain in dimension n. Okay, so let's do the regret analysis. So the regret of this is bounded by what? Okay, so you have a Bragman term, which we're going to worry about in a minute. So you have dy x1 over eta. And then you have a term which is exactly the local norm, again with the entropy. But now the local norm with the entropy, they are just the sum. So let's say we have 2 eta, the sum for t equals 1 to capital T. And here what you have is xt dot lt squared. Okay, see the difference. Here it was pt, where pt is the exponential weight, is this element of, I shouldn't have erased it. So you have delta A and convex hull of A. Okay, so this is Mero descent with the entropy, and this is multiplicative weight. So here, the local norms are pt dot the L-Chech, and here the local norm is x dot lt. And you see where you win is that now you're squaring something which is between 0 and 1, whereas before you were squaring something which was between 0 and m. Okay, so you win in the variance. The variance become better. So this term now is bounded by 1. And I'm probably making a mistake when I say that. I feel like I'm making a mistake. Yes, it's bounded by m. Okay, each entry of LT squared is smaller than LT, and xt dot LT, so maybe it's smaller than xt dot LT, because the LTs are in 0, 1, which is smaller than m by the assumption, okay, because xt is a convex combination of things which have L1 norm m. So instead of m squared, we got m. Okay. Now we have to worry about the Bragman divergence term. Okay, so what is the radius? So what is the radius of a convex hull of things which have L1 norm m when you look at the entropy? So what is the radius? What is the Bragman radius? Okay, so you remember yesterday I told you that d phi between y and x1, if you choose x1 to be the minimizer of phi on your convex bodies, and this is smaller than just phi of y minus phi of x1. This is just x1 is the argmin of phi of x when x is in k. Okay, so you just need to bound these two terms. Now, we're taking the entropy, right? So phi of x, again, is the sum of xi log xi. Every entry is between 0 and 1, so this is negative. Okay, so we only need to worry about minus phi of x1, which is this sum of, let's say, xi log 1 over xi. Phi equals 1 to n. And the sum of the xi, okay, I'm sorry for this, I put 1 and then the index here. I hope it's okay. You won't, okay. So now, what do you want to do? Okay, you just want to use Jensen at this point. Okay, you just want to use that minus log x is convex. Okay. So what is this? I'm just going to write it as the L1 norm of x times the sum of xi over the L1 norm of x, log 1 over xi, for I equals 1 to n, right? So this is the, so minus log is like this. Now this value is, let's see, what am I saying? I want to say, no, sorry, I just want to use log. So I want to use that log is concave, okay? So what is this thing? This thing is the average of values of log. So it's below log of the average, okay? So this is smaller than log of the average of those things. And you see the xi's, they cancel, and what I will get is n over the L1 norm. So this is smaller than the L1 norm of x times log of n over the L1 norm of x. Okay? Which is exactly, by my hypothesis that the L1 norm is m, this is equal to m log n over m. Okay, so we find that the Bragman radius with the entropy of this convex cell is exactly the same as the log of the size. I mean, not exactly. This is an upper bound, but we find this. Okay, so what do we get? So this was, again, this one was RT of multiplicative weights. Now we get that RT of Mero Descent is bounded by m log n over m over eta plus 2 eta Tm. Okay, so when you optimize and you ignore the log, what you will get is m times square root t. And this is clearly the best you can hope for, m times square root t, because in this setting, one simple example would just be that I have m independent games. Imagine that I have my interval. This is like all the coordinates. I have n coordinates. I can divide it into chunks of size m. Okay, so I have n over m chunks of size m. Now, I could have just, my set of concept is that in each one of those chunks, you have to pick one element. What does this game mean? It exactly means that I have n over m independent games of size m. And probably I want the other way around. I want this of size n over m, and I want m chunks. So now I have m games. Each one has n over m elements in it. Okay. So the best you can hope for is going to be, so the lower bound is clearly m square root t log n over m. This is the lower bound that you get on each one of those games, and they add up. Because there is no correlation between those different games. They are just completely independent. So this is the best you can hope for. It's matched by Mero Descent. Now one question, so this was observed, this observation was made in Cullen, Warmus, and I always forget who is the last guy. And Kivinen in 2010. Okay, so they just observed that in this combinatorial setting, using Mero Descent, they didn't phrase it like this, but that's what they were doing, using Mero Descent with the entropy is indeed better than doing multiplicative weights. Now, you might ask, okay, but maybe I can improve the analysis of multiplicative weights. So we proved then later a theorem. So this is Jean-Yves Audibert, myself, and Gabor Lugosi in 2011. We showed that, I will just make it informal, that the analysis of multiplicative weights is tight. Okay, so this bound, you cannot improve it. It's just the best you can do. Both terms, they have to be there. Okay, so Mero Descent, now we see that it has a real advantage. Yesterday we saw that by playing with the mirror map, even on a simplex, you could improve results for the bandit game. But now we see that even in full information, there is an advantage to using Mero Descent. Is there any question on this? Now I'm going to do an extension to a partial feedback model, which is not fully bandit, but in between bandit and full information.
Is there a way to extend this to the case in which the losses are greater than 1? Maybe some...
Yeah, so of course, if the losses, if they are between 0 and b, then you will just multiply everything by b. But you might ask, okay, one good question to ask would be, what if the normalization, instead of being per edge, you have a normalization for your total loss? Meaning that the adversary, instead of choosing, in my example of the graph, instead of saying that he can put a unit loss on every element, what if he can put a unit loss on every pass? Okay, in total. Then it turns out that in this setting, Mero Descent and multiplicative ways get the same bound. So what Mero Descent really exploits here is that there are edges, and that the normalization is not the same if you have a unit loss on each edge or a unit loss in total. Because if you have a unit loss in total, you could put, maybe m loss on the last one, for instance. You can concentrate everything on one edge. What this normalization tells you is that the adversary has to disperse its losses. If you pay a loss of m, it's because you have encountered many edges with loss of 1.
So you don't get like a square when you are normalized that makes things like before.
No. Yeah. Yes. Yes. Exactly. Yeah. Okay. Okay. So now let's move to partial feedback model. So this is a semi-bandit model. I will attribute it to myself, but there are many papers who were doing something like this before on specific instances, on specific concept class. What we did was merely, identify that there is a general problem on all, which generalizes all of those things. So the model is like this. Of course, in bandit setting, you choose your ST path. What you would observe is just, okay, what is my total loss? But there is a smarter thing, there is something in between, which would be I choose a path, and maybe I can observe the loss on every edge in that path. Okay, so the semi-bandit feedback, let's say model, is that you observe the vector LT of I, AT of I. Okay, so remember AT of I is either 0 or 1. So what this means is that for every edge that you picked, you observe the value of the loss. Okay, so this is much more feedback than bandit, where you would observe just one number, but it's also much less than full information, where you observe all the edges in the graph. Okay, so you observe, so these are how many numbers this is? This is m real numbers. Okay, so instead of observing n real numbers, we observe m. So it's a gap. So it's n over m times less than in full information. Okay, so we have n over m times less observation than in the full information model. So we expect a regret of what? So before we had m square root t. So here you expect m square root t times n over m, which would be square root of t and m. Okay, this is what you would expect just from purely information theoretic perspective. What I mean is, again, I don't want to talk about statistics too much in this course, but what this means is that you can prove this lower bound, basically. Okay, you cannot do better than square root t and m. And what I will show to you now is very simply that Mero Descent satisfies this. maybe, okay, I will keep this. Okay, so the idea, just like yesterday in the bandit case, is to have an estimator for the losses. Okay, so what is a good estimator? So estimator L tilde t for LT in this model. So here is what I propose. L tilde t on location I. So of course, I want it to be LTI, but it's only going to be LTI if I do observe, it. And what I need to do is, just like yesterday, I need to renormalize by the probability of observing this coordinate. What is the probability of observing this coordinate? It's the expectation of this coordinate. But the expectation of AT is xt. So the expectation of this coordinate is just xt of I. So this is just normalized by xti. Okay, for any I in 1 to n. Okay, so if I did not observe an edge, just like yesterday, I estimate to 0. And if I do observe it, then I just renormalize by the probability of observing. Okay, this makes sense, I think. Notice that the expectation of L tilde t is LT. Okay, since the expectation of AT is xt. Okay, by definition, so remember what we're doing. We're running Mero Descent on the convex hull of A. What we get is a point xt. Then we find a distribution such that the expectation of a point sample from this distribution is equal to xt. And my loss estimator is just my observation divided by these coordinate values. So now let's see what is the variance of this thing. Okay, the only thing we need to calculate is this thing. So the question is, what is the variance? This is always the question, the important question that you have to worry about. What is the variance? So the variance is this term. It's the expectation of xt dot L tilde t squared. Okay, so in other words, it's the expectation of the sum for I equals 1 to n of x ti times LTI ATI over xti and this squared. Okay? So just like yesterday, in the multi-arm bandit case, we see that we have one xti that cancels with the other one. Okay? Of course, LTI, we're going to bound it by 1. And ATI squared is the same thing as ATI. So we get that this is bounded by the expectation of the sum for I equals 1 to n of ATI over xti. But the expectation of ATI is xti. Okay, so this is equal to n. So I really, really like this type of calculation. I mean, it really works just perfectly. Okay, so the variance of Mero Descent, the local norm, of those L tilde is exactly n, the dimension. So what you find, so this implies a regret, which is of the form, let's ignore the log. So the first term is m over eta. And the second term, we get t, and we get t eta n. So you see, we replaced an m by an n. Okay, so when you optimize, you get that this is square root t and m, which is indeed the best you can hope for, and it's achieved very simply. Okay, so this semi-bandit model is simple. Any question on this? So now next, what we're going to move to is the bandit case. Okay, in the bandit case, we will just observe a single number. So if you observe a single number, using this reasoning, what you expect is, you observe one real number, so it's n times less. Okay, so you expect to have m times square root t. And in fact, it's going to be more subtle than this. So that's the interesting and surprising part. Okay, maybe I will erase this. Everybody has this in mind. This theorem, you know, the Bragman radius, the local norms, and you need the well conditioning. Okay, so let's do a heuristic calculation in the bandit case. And I will explain why it's a heuristic. So the big question in the bandit case is that you have this single number. What do you do to get an estimator, you know, for all the entries? So what you do is what is called one-point linear regression. So one-point linear regression estimator. And this is after Danny, Ace, and Kakade. A really beautiful paper from 2008. It goes like this. So again, what do we observe? So we have played AT from some mu t. And what we observe is LT.AT. Okay, that's the only thing we observe. So what I'm going to do, let me use just to simplify what I'm going to do. Let's write this as AT transpose LT. So now let me denote sigma t is going to be the second moment of this distribution. So this is going to be the expectation when A is sampled from mu t of AA transpose. This tells me about the covariance of my distribution. Okay? It tells me about correlation of different entries. And what I need to do to unentangle what is LT out of an observation of AT is use those correlations. What do I mean by this? So let me set L tilde t is going to be the following estimator. It's going to be sigma t inverse AT transpose LT. Okay, so it's really a very nice formula. So let's see what happens. So let me assume that sigma t is invertible. That's not a problem. I can, as long as my convex body is of full rank, I can just add, you know, a little tiny epsilon everywhere so that it's invertible. It's just that if it's badly conditioned, then the variance is going to be terrible. So I will need to worry about that. But let's see what is the expectation of this thing. The expectation when I sample AT from mu t, well, the only thing which is random, which depends on AT, you know, this is known. This I can calculate. This thing is known. It's a real number. The only thing which is random is this. So when I take the expectation of AT transpose when AT is sampled from mu t, this becomes sigma t. And it cancels with sigma t minus 1, and I find LT. Okay, so the expectation when AT is sampled from mu t of L tilde t is equal to LT. Okay, so it's really, really nice. It's a non-biased estimator based on a single point. Now, of course, as always in those bandits, in this bandit business, you have to worry about the variance. But here it seems even more difficult, you know, because this sigma t inverse, as I said, you know, it could have a very small eigenvalue, which really messes things up. So we have to worry about that. So now let's do the variance calculation of this thing, and you will see that it just works again. So variance calculation with multiplicative weights. Okay, so now I'm not going to do Mero Descent. I'm going to do multiplicative weights, and I will explain to you in a minute why I do that. Okay, it's a little bit of a subtle point, but okay. Now I do multiplicative weights. So let me define just before to clarify. You know, this L tilde t, this is a vector in Rn, but because I'm working with multiplicative weights, which is defined on the set of vertices, it's nice to think about this as a function on the set of vertices. And so to clarify, let me introduce a notation. So L tilde Czech, or maybe Czech tilde, well, yeah, that makes more sense. Czech tilde, okay, it doesn't matter. Of A, this is L tilde T, okay, I tilde Czech. This is L tilde T dot A. Okay, that's just so that I have a function which is really defined on the set of vertices. Now, what is the variance that I need to worry about? The variance is the expectation of mu t. I don't know why I called it mu t and not pt, but okay. Mu t inner product with L tilde Czech t of A, L tilde Czech t squared. Okay, this is what I need to worry about. Okay, so what is this thing? This is the expectation of the sum over all actions of mu t of A times L tilde t Czech of A squared. Okay, that's the definition of this inner product, which is nothing but the expectation of the sum over A of mu t of A times L tilde t transpose A squared. Okay, that's just so this is a variance that so far I did nothing. I just did some rewritings. So let me continue with the rewriting. This thing, you know, it's a real number time itself. So you know I can apply the transpose. So this is L tilde t transpose A transpose L tilde t. And why did I rewrite it in this suggestive way? Because the sum of the mu t A transpose, this is sigma t. Okay, so this is equal to the expectation of L tilde t transpose sigma t L tilde t. By the way, again, it's always, so the common theme of those 4 lectures is that I'm doing some magic and then I explain the magic. Okay, so right now this will be some magic, and then we will see that there is a very nice explanation in terms of an object which is called the entropic barrier. And this will clarify all this calculation. But right now, okay, we have this calculation. So we find sigma t that appears. So here, the way I want you to think about it is that this is again a local norm. Okay, this is a certain Euclidean norm where the matrix, you know, that does the transformation is this covariance matrix. And the entropic barrier is exactly going to be a function whose inverse Hessian is going to be this covariance. So this will exactly, again, be a certain Mero Descent. So these multiplicative weights will correspond to a Mero Descent, but just a more complicated Mero Descent. Okay, but in any case, let's continue our calculation. So we want to bound this. Now, what is L tilde t? Okay, so we have this thing, which is a real number, which is bounded by m. Okay, this is bounded by m. So what do we get? We get this is bounded by m squared. And then we have the expectation. And what do we have? We have, so L tilde t is sigma t minus 1 at. Okay, so we get sigma t minus 1 at transpose sigma t minus 1 at. You see that sigma t and sigma t minus 1, they cancel. Some magic happens here. And what we find is now, instead of a certain local norm or dual local norm of the L tilde, we find a primal local norm of the AT. So what this is equal to m squared, the expectation of AT transpose sigma t inverse AT. Okay. Right? So this was a dual norm of the L tilde, and now we have a primal norm of the AT. But now what is this? Okay. Again, this is a real number. Okay, so let me do this calculation. The expectation of AT transpose sigma t inverse AT. Okay, this is a real number, so it's equal to its trace. This is expectation of the trace of AT transpose sigma t inverse AT. Now by cyclic invariance of the trace, I can put my AT here. Okay, so this is equal to the expectation of the trace of sigma t inverse AT transpose. But now the expectation, it's the expectation over what? It's the expectation, you know, always, it's the expectation over the sampling of the action. So it's the expectation over AT sampled from mu t. Now the expectation when AT is sampled from mu t of AT transpose, it's sigma t. So this expectation is sigma t. So this is equal to the trace of sigma t inverse sigma t, which is the identity. So this is n. Okay, we find the same thing as before. The variance is also n. Okay, except that, okay, here it was n, now it's n times m squared. Okay, so what we get now is that the regret is bounded by log of the size of the action set. We're doing multiplicative weights over eta plus eta t m squared n. Okay, so when you optimize and you use that the log is basically m, yes, please. Here? Yes. Yeah. So you see the sum, so I can, by linearity, this L tilde T transpose, I can put it outside of the sum. Yeah. So I just have inside the sum over A of mu TA, A transpose. And this is sigma T. Right? Sigma T is the sum of mu TA, A transpose, by definition. Okay, maybe before I continue, is there any other question on these calculations? Okay, so what you get, so again, using that the log of the size of A is basically m, you get up to a log factor. This is, so you get the geometric mean, so you get m to the 3/2 square root t n. Okay, and remember that my little argument that I was saying before, if you have, you know, you have n less information in bandit, whereas in semi-bandit you had n over m less information. So my expectation was that I would get m square root tn. Okay, expectation. We could get m square root tn. Okay, this is also, so it's natural from the lower bound perspective. It's also natural from the upper bound perspective because here we just use multiplicative weights. And we just saw, you know, in full information and semi-bandit, okay, I didn't do the calculation in semi-bandit, but certainly in full information, we saw that by doing Mero Descent, you know, in this geometric perspective, you could win a square root m. So in 2011, I conjectured that you could get this bound, and last year it was disproved. So let me state the theorem. So this is tight. So theorem. So this is by Cohen and Hazan from 2017. This is not the Michael Cohen who is on my papers, and this is not the Hazan who is on other papers. These are different guys. Is that lower bound of m to the 3/2 square root tn. Okay, so you cannot beat this bound, which is, I still find it very surprising, but okay. It's actually correct. The proof is correct. So there is something funny going on here, and I don't want to talk more about that aspect. What I want to now talk about is the fact that this is not true. So maybe let me use another. Not true. Why is it not true? It's not true because this guy, this L tilde T, can have negative entries. So the well conditioning of the entropy is not satisfied. Okay. L tilde T can have and will have negative entries. So well conditioning assumption not automatically satisfied. And this is not it might look like a small issue, but it's not a small issue. So there were papers trying to go around this. So for the entropy to be well conditioned, okay, it's automatically well conditioned when the loss that you have are non-negative. But it's also well conditioned if the magnitude of the entries is not too big. So it's okay to have some negative entries as long as they are not too negative, not too big. So what people were doing is that they were adding extra artificial exploration in the process. So instead of playing from mu t, they would play from 1 minus gamma mu t plus gamma, let's say, nu, where nu was some fixed distribution to explore, the set of action as much as possible. And this little gamma was set so as to ensure that the entries don't get too small. Because why would they get small? It's again because of the smallest eigenvalue of this sigma t inverse. Okay, so this was a way to prevent the smallest eigenvalue to get too small. The problem is exploration in those combinatorial spaces is not an easy problem. Think again about this grid example. Okay, so in this grid example, you see, okay, one naive way to explore would be just to take a concept at random. But if I take a concept at random, this edge is explored with exponentially small probability. Okay, the probability at random to encounter this edge is 1 over 2 to the m. Okay, or 1 over 2 to the m over 2. Okay, if this is m over 2 by m over 2, and each time I go either right or up with probability half, the probability when I explore randomly to get to this edge is exponentially small. Which would mean if you just do a naive exploration, then the smallest eigenvalue could be exponentially small, which in turn will show that, this well conditioning, it's really bad. Like it's exponentially bad, the conditioning. So what you need to do is to do something smarter. And there are ways to do something smarter. So I will just mention one idea, which we will not prove in details, but just to give you some. So this is like an aside. I just find it interesting. But then we will do the entropic barrier, which gives you automatically a good exploration. So aside, smart exploration. So smart exploration, it goes like this. Think of it as points. The key idea is to think of it as point in Rn. Okay, so this is my set, the convex hull of A. And you see, what this is doing really geometrically is that you have a very sharp corner. Okay, and in this very sharp corner, you have this direction. That's really what this means. So the idea is geometrically to look at what is called the Loevner ellipse. So you look at the smallest volume ellipse that contains your convex body. Okay, this is a Loevner ellipse. Now there is a beautiful theorem by John that the Loevner ellipse, it touches your convex body at certain vertices. And in fact, there is a distribution over these contact points which is almost isotropic, okay, which has a smallest eigenvalue which is not too small, which is basically 1 over the dimension. Okay? So you can take this distribution as an exploration distribution. Now, of course, it's computationally hard to find this ellipse, etc. So doesn't really give you an algorithm. So this we did, this was myself, Nicolo Cesabianchi, and Sham Kakade in 2012. Okay, so this allowed us to make this statement true and get the optimal bound, but I don't find it very satisfying. So what I'm going to tell you now is a more natural approach, which was put forth in the groundbreaking paper by Jake Abernethy-Hazan and Sasha Rakhlin, which connects Mero Descent with interpon methods. Because this problem of having a well-conditioned barrier actually appears already in the literature in interpon methods. So now what I'm going to tell you is I'm going to do a, I don't know, 1 hour, okay, maybe less than 1 hour, 45 minutes crash course on interpon method, and then we'll see how it's relevant for bandits. Okay, so that's where we're going. And I think I can do it in 45 minutes, but please stop me and ask me questions to slow me down. Okay, what's the number? 5. A small detour through interpon methods. Okay, so what are interpon methods? So now I'm gonna forget a little bit about this combinatorial setting and just I want to generalize the discussion to bandit linear optimization, meaning that we have a convex body, we have to take a point in the convex body, the adversary chooses a loss vector, and we just observe the inner product. So what is this? We have a convex body, and what we care about, so the objective, we get a convex body and an objective function c, and we want to minimize c dot x subject to x is in k. Okay, so for instance, if k is a polytope, this is a linear program. If k is a affine constraint on matrices plus a semi-definite constraint, this is a semi-definite programming. You have hyperbolic programming. Okay, you have many type of things that are contained in this. Now, the difficulty is, of course, this hard constraint. Okay, so a natural thing to do is to try to relax this in some ways. So this falls in the framework of barrier methods. So given phi, let's say from k to r, convex, or r bar, taking value in r bar, convex, and such that phi of x tends to infinity as x tends to the boundary of k. Okay, so what you have is you have this convex function on your convex body, okay, and it blows up when you get close to the boundary. Okay, it's really a barrier function. What we're going to do is that we're going to replace this minimization with a hard constraint by minimization of this plus phi of x with a certain penalty on phi of x. So what we do is now consider x of t at time step t, which is the minimum or the argmin of t times c dot x plus phi of x. And now think, let's say this is all of Rn maybe. It's just plus infinity outside, so over x in Rn. So you essentially moved from a constrained minimization to a non-constrained minimization in some sense. Okay, and you see at time 0, I'm just minimizing phi. And at time infinity, I'm putting all the importance on minimizing this objective. So it makes sense, and we'll prove it, that at time infinity, I'm going to get to the minimizer. Okay, so this is called the central pass. And the picture is like this. If I have my C, which is like that, or maybe it's the other way around. This is C. So if I want to minimize, I want to get to this point. Okay. This is x at time 0. And now I have some path like this. Okay, I don't know. It's doing something. And eventually it gets to this corner. And what we want to do is to follow this path. Okay. And And I will just need to remind you one thing about convex optimization, which is how does gradient descent on well-conditioned functions. So just a reminder. If you want to minimize f of x over x in Rn with f such that the spectrum of f, of the Hessian of f, let's say, at any point x is included in some, okay, what I mean is just the spectrum of the Hessian is included in some interval alpha beta. Okay, alpha and beta are two positive numbers. So this is, in the literature, this is called alpha strong convexity, and this is beta smoothness. Okay, so all the eigenvalues are not too small, and they are not too large. Okay? So by this notation, I mean, you know, the set of eigenvalues for all the points in the space. Okay? Then, gradient descent reaches the minimum, reaches the epsilon opt point in kappa log 1 over epsilon, where kappa is the condition number, which is the ratio of beta to alpha. Now, kappa is beta over alpha. So a well-conditioned problem, it means that it's very close to a quadratic function. Okay, if alpha and beta, I mean, no, that's not what I meant, sorry. A quadratic problem can also have a very bad conditioning number. But okay. So this result, I won't reprove it. It's just it's literally 2 lines. I will leave it as an exercise. And to simplify the presentation of interpond method, let me assume that I can remove this. By this I mean, you know, if you don't want to deal with numerical accuracy problems, you can reach machine accuracy. You know, this is a constant. You know, you can reach 10 to the minus 16, and this is just a factor 16. Okay, so I want to say now, to simplify the presentation, that you can literally get to the minimum, to the actual minimum in kappa iteration. And this will, to me at least, dramatically simplify the presentation of interpond methods. Okay, so let's do that. So now, now what? So now I want to move. Now, let's assume I do this idea of following this path. So let's assume that I'm at some point x at time t. Okay, let's assume that I found this. And now I want to move to x at time t prime for some t prime bigger than t. And what I want to say is that if on this region this function is well conditioned, then I can, and now when I say well conditioned, I mean that the condition number is a constant. Okay, so if phi is well conditioned in this neighborhood, then I can just use gradient descent to move from x of t to x of t prime in a constant number of iterations. So let's see that. Now, say we are at x of t, and let me introduce a notation for this. Let's call this phi sub t of x. And we want to find xt prime for t prime bigger than t. Okay, and assume that the Hessian of phi is well conditioned on some ellipse that contains xt prime and centered at xt. Okay, so the picture again is that is this picture. I have x of t, and let's say I can find some ellipse where I know that xt prime is included in this ellipse, and on this thing, the Hessian is well conditioned. What do I mean by the Hessian is well conditioned? It's not what I said before, but what I mean is an ellipse, let's call it E. Assume that, so it does. The Hessian phi of y is roughly the Hessian phi of x for any y in E. And this is x of t. Okay, so what I want to say is that the Hessian does not change too much in this neighborhood. If that's true, then what I can do is that I can compute the Hessian at this point and then run what is called preconditioned gradient descent. So really notice that this theorem, it's very easy to modify it. So how could I modify it? Let's say that, a modification would be to say, let's say that the Hessian of f at any point x is between beta times some sigma and smaller than alpha times sigma. Then what you can do is you can do preconditioned gradient descent with sigma inverse. And you just change the geometry so that sigma becomes the identity. Okay, so if you know a matrix that sandwiches your Hessian everywhere, then it's essentially as if it was well conditioned. The same thing. You just need to do calculation with sigma inverse. If you have never seen those things, I don't expect you to see it immediately, but just it will be worth your 5 minutes after the course to check it, okay? That if you precondition by sigma inverse, so by preconditioning, I mean that instead of minimizing f, you look at g of h, which is f of sigma inverse, sigma to the minus 1/2 x. Okay? You look at this function, you take the Hessian, and you will see that it satisfies this guy, g is well conditioned. Okay, so if f satisfies this, then g is alpha strongly convex and beta smooth. Okay, just change the geometry with sigma to the minus 1/2. So you can do this here. If the Hessian is well conditioned in this neighborhood, you can now just run preconditioned gradient descent using this information. So just so you know, if you go look also for interpoint literature, they will make a big deal of using Newton method. What is Newton method? Newton method is nothing but the first step of preconditioned gradient descent with this type of preconditioning. Okay? And in this literature, because they really care about applications, they make also a big deal of doing one step of Newton method, whereas what I'm doing here is that I'm doing many steps of this preconditioned gradient descent. So it's less applicable than what those guys are doing, but it's much, much, much simpler mathematically. But also we make this modification. Anyway, I'm trying to talk to two public right now, the experts and also everybody who wants to learn about this. So ask me a question if what I said was not clear. I'm going to continue this. Yeah, please.
So in general, how do you guarantee that you stay inside?
Okay, yeah. So I don't want to talk too much. Okay, I don't think this through completely. But I think you can do that. I think what you can do is that if you know this ellipse and you know that the optimum is here, then what you could do is, if you do step outside, then I just want to extend, do like a minimal quadratic extension of my function outside of this convex body. So what I can tell you is that I know how to do this, if maybe this was a cube. For an ellipse, it seems a little bit more complicated, but I think you can do it. Maybe let me say something else. Maybe you can do projected preconditioned gradient descent. So if you do step outside, you just project back on the ellipse. Maybe, I don't know. It could be. Yeah, this is not written anywhere, but it seems to make sense to me. Yeah, maybe it's related to this. I don't know. Okay. Yeah, please. Many questions.
Is this equivalent to this Newton type approach?
Yeah.
Do they follow roughly the same?
So when you do preconditioned gradient descent, the first step is exactly Newton method. But then the following step are not Newton method. The following step, you don't update the Hessian. You just keep the Hessian of the first step. So it's a bit cheaper, the following steps, but on the other hand, practice people do one step, right, and then update temperature parameter. Okay, so the big question we need to answer right now is, what is the big question? So there are two big questions. One of them is, how do we ensure this? Okay, because remember that phi is a barrier function, so it blows up at infinity. So the Hessian, when you get close to the boundary, is changing very quickly. Okay. So what is this ellipse on which I have this well conditioning? And so here is the genius of Nesterov and Nemirovsky now. So definition. Okay, I should say this goes back to Karmakar in '84. Okay, and this was a big deal back then. I mean, it got a New York Times article, and so it's a deep learning of the '80s. So Nesterov and Nemirovsky. So phi is self-concordant. Essentially, phi is self-concordant if E is the ellipse which is defined by the Hessian itself. So let me write this. If one can take E equals the set of points x plus h such that the local norm of h is smaller than, let's say, a half. Okay, so again, what I'm saying is this ellipse on, my function will be well conditioned, it has to get smaller and smaller. Because as I go close to the boundary, the function phi is changing more and more rapidly. And what Nesterov and Nemirovsky said is, I'm going to define a class of function where this well conditioning holds on the most natural ellipse that you can think of, which is, the ellipse, which is a unit ball in the Riemannian geometry, induced by phi itself. Okay. So something that I find easier to work with than this definition is a certain inequality that I'm going to write right now. So this is roughly equivalent, it's certainly implied by the following differential inequality. If I take the third order derivative of phi at x in the direction h, h, h. Okay, so let me just remind you something. So this is a Lipschitz condition. Okay. Lipschitz condition means that the derivative is bounded. So if the Hessian is Lipschitz, it means that the third order derivative is bounded. If this was true on the Euclidean ball, I would write that this is smaller than the Euclidean norm of h cubed. Now what I'm going to write is that this is smaller than the local norm of x cubed. Okay? And let's put the factor 2 so that minus log x verifies this. Because this factor 2 is arbitrary right now. So this is the definition of self-concordant. So if you have a function phi that verifies this inequality, then it's it's well conditioned on those natural balls. And so you can run this program provided that you take t prime such that x t prime is close to x of t. So the next question at this point is, how much bigger can be t prime compared to t? So question. So of course, I want to take t prime as big as possible, right? I want to make progress as fast as possible on this central path. So how much bigger? How big can be t prime? So that, what do I want? I want the local norm of xt prime minus x of t in the local norm at xt to be smaller than some constant. Okay, that's the calculation I want to do. Okay, so what do we know about xt and xt prime? Well, what we know is that they are minimizer of these functions. So we can write the first order optimality condition for this. Okay, so first order optimality condition. So first order optimality condition tells me that the gradient of phi at x of t plus t times c, this is equal to 0. Okay, so I know something about grad phi applied to x. So I know something about xt in the dual. So now what I'm going to use is my intuition that, this distance, the primal norm in the dual corresponds to the dual norm. The primal norm in the primal corresponds to the dual norm in the dual. Okay, so what I want to say is that this thing, this is roughly equal, and you can make this precise provided that the function is self-concordant, to the norm of grad phi at xt prime minus grad phi at xt, local norm at xt, but dual. Okay, so why is this identity true? Again, one way to think about it is that this is essentially, if the function is well conditioned, this is essentially the Bragman divergence between those 2 points. And you remember I told you this identity, this nice identity, that the Bragman divergence between x and y, this is the Bragman divergence of the Fenchel dual between y and x. Sorry, grad phi. Grad phi. Okay, and this is roughly like the norm of x minus y at x, and this is roughly like the local norm of grad phi of x minus grad phi of y, local norm at x dual, and with squares. Okay, so this is the way I think about this. Okay, and if you want, you can just work out the identity or a bound on this, an upper bound. It's easy, using the self-concordance. So now that we have this, and we know that this is equal to the norm of, okay, so what I want to say, you see, grad phi of xt, it's tc, and with a minus, and grad phi of xt t prime, it's t prime c. So this is t prime t, let's see, t, what do I want to say? I want to say t prime. So this is t prime over t minus 1 times grad phi of xt local norm at xt. Okay, this is what this is. So now we see what kind of t prime we can take. So if I write, t prime is, so say t prime is 1 plus epsilon times t. I'm trying to increase things multiplicatively. Then this is epsilon times the norm of grad phi of xt, local norm at xt dual. So we see that t prime, I can take it as big as 1 plus 1 over this local norm. Okay, but these local norm, what is their values, Maybe they get very, very big. So my next assumption is that they don't get too big. So this is called new self-concordance. So definition. So again, Nesterov and Nemirovsky. Phi is new self-concordant if, for any x, the dual norm, the dual local norm of grad phi, let's say with a square, is bounded by nu. Okay, so it's just an assumption. So if I have this, then I know that I can take t prime to be 1 plus 1 over square root nu. Okay, so this implies that t prime equals 1 plus 1 over square root nu times t is a valid choice. So next I want to just state a simple lemma, which is the following. C dot x of t minus y for any y, including opt, this is smaller than nu over t. I won't prove it because of lack of time, but it's a super simple calculation using the definitions. So this is assuming that phi is nu self-concordant. You can ask me after the lecture and I will explain this to you. Or maybe should I prove it? Should I prove it? Do you want to see a proof or it's okay? So okay. Y is any point for any y in K. Of course, I'm thinking of taking y to be the minimizer of C dot x. That's the one for which this inequality is the strongest. Okay, but proof or no proof of this? What? No, it's like 5 minutes. So. Okay, why not? Okay. So here is a. Okay. So C. So what is C? C is just, you see, this is equal to, let's see, this is equal to grad phi of x of t dot y minus x of t with a 1 over t. Okay, C is minus 1 over t grad phi. So I just change this and I get 1 over t. So the only thing I need to prove is that grad phi of x dot y minus x is bounded by nu. So let's do this. So we need to show, yeah, maybe it's a good exercise actually. So we need to show that grad phi of x dot y minus x is bounded by nu. That's what we want to show. Okay, what is this? So let me introduce, it's easier to work with one-dimensional function. So this, I'm going to say that it's psi prime at 0, where psi of t is just phi of x plus t times y minus x. You see, when I differentiate this, I get the gradient of this inner product with y minus x. And at 0, the gradient of this is the gradient at x. Okay, so this value is psi prime at 0, where psi is just, I'm just at x. Okay, the picture, just to clarify. I have some point y, which, as Nicola said, it's some vertex, okay, basically the optimum. And we look at the function on this line. Okay, we're sitting at the point x, and we're looking at how the function is behaving as I move over there. And the value I just want to say is that the derivative here is always bounded by nu when I look at this distance. So of course, when I get closer, the gradient gets bigger, but my distance gets smaller. Okay, so the intuition, maybe I should say that also, the general intuition is that those self-concordant barriers, they behave, the gradient behaves like 1 over the distance to the boundary. Okay, which is exactly what this is saying. Okay, so let's see that. Okay, so what do we know about psi? Well, we know that it's self-concordant, nu self-concordant. So we know this. So we know that psi double prime of t times psi prime of t squared is bounded by nu. I made a mistake. This is a minus 1. Okay, this is a dual norm. Okay, so the dual norm is the inverse of the Hessian. Okay, so these two things are the same. Okay, so we know this. So what is this? This is the same thing as minus 1 over, okay, I want to do it the other way around. So this is the same thing as nu is smaller than psi double prime of t over psi prime of t squared, 1 over nu. And what is this? This is just minus 1 over psi prime of t prime. Okay, it's just this derivative. So now I can integrate this. So if I integrate over a window from 0 to t, I get t over nu is upper bounded by, okay, the value at the end minus the value at the beginning. So this is 1 over psi prime of 0 minus 1 over psi prime of t. Okay. Good. And now I can just rearrange those things. And I want to say I get 1 over psi prime of t, which is upper bounded by what? So I get minus, I get nu, minus, okay, maybe let me write it right now, I'm struggling. 1 over psi prime of 0 minus t over nu, which is equal to, nu minus t psi prime of 0 over psi prime of 0 times nu. And now I'm done. Why is that? You see, this does not get to 0, at time t. Because what I want to say is that x plus t times, okay, what am I saying? What am I saying? There's a sign error. Where is it? That would be good. Is it? If I take this on the other side, no, I want to say, what do I want to say? Yeah, okay. Yes, okay, very good. What, at time 1, okay, now I need to use psi prime of 1. This is less than infinity. Because at time 1, I'm at the point y, which is still in my convex body. Okay, so in fact, yeah, I need to be a little bit careful and say that this y is just a little bit inside. It's just in the interior. Doesn't really matter, because there is nothing that depends on y on the right-hand side. So at time 1, this is infinite, meaning that this is not 0, meaning, that nu minus psi prime of 0, this is positive. So psi prime of 0 is smaller than nu. Okay, let me just pause for a second. Okay, so I'm just using the fact that this has not, at time 1, it has not blown up. Okay, so this is some positive quantity. If it's a positive quantity, it means that this is positive. Okay, so this is positive, so psi prime of 0 is smaller than nu. And psi prime of 0 is what we wanted to bound by nu. Okay, and then, this kind of proof is exactly how you prove everything in this theory. Just little manipulation like this. But the intuition is what I wrote over there. Okay, so now let's conclude this thing on interpond methods. So you see, you get to nu over t. Okay, So we can do, so what is the conclusion? So move from xt to x1 plus 1 over square root nu t in one Hessian calculation and O1 gradients. Okay, so this is one step. One step takes me one Hessian calculation of my barrier and a constant number of gradients. And you move from t to 1 plus 1 over square root nu t. And what we know is that at t equals nu over epsilon, we are epsilon optimal. Okay, because of this lemma. If t is nu over epsilon, then we're epsilon optimal. So to get to this point, at rate 1 plus 1 over square root nu, starting from a point, say, at time 1, what you need to do is a log number of steps. Okay? So this means from x1, x at time 1, log nu over epsilon, log, so square root nu times log 1 over nu over epsilon step, and we are epsilon opt. Okay? And where did this square root of nu comes from? It comes from, because we take the log in base 1 plus 1 over square root nu. Okay, so if you do square root of nu log nu over epsilon step, then you get 1 plus 1 over square root nu to this power, and this gives you nu over epsilon. Okay, I think it's fair to say that this is a state of the art of linear programming, which is like maybe the most important application of applied mathematics, to this date. So it's a bit crazy to me. You can do various refinements, some of them pretty recent, many refinements actually, but essentially from a purely theoretical perspective, this is a state of the art. We don't know how to beat this behavior. So one big thing that I have hidden right now is, do those functions exist? Okay, so that's what we're going to talk about right now. But before I erase, is there a question on this? So again, if you have a self-concordant barrier with parameter nu, self-concordance parameter nu, then you can run this algorithm that I told you for a number of iterations, which is essentially just square root nu, and you will get to the optimal point. Okay, so if nu was a constant, this would be a very, very good algorithm, just a constant number of iterations. Now, of course, the complexity of an iteration is the calculation of the Hessian of this barrier. So the barrier needs to be simple enough so that you can compute it. Okay, so now about the existence, here is a theorem from Nesterov and Nemirovsky in 94, is that there always exists, for any k, there exists O of n self-concordant barrier. So in dimension n, you can always find a self-concordant barrier whose self-concordance parameter is of order of the dimension. And this is the state of the art that I was talking about, is that we don't know how to improve, even essentially discarding some computational aspect, how to improve this square root n number of iterations, square root of the dimension. Now, the barrier that those guys constructed, it's called the universal barrier, and it's not an efficient barrier. It's not easy to calculate the Hessian. In fact, calculating the Hessian is basically as difficult as solving the original problem. So this shouldn't be viewed as giving an algorithm, but it tells you something about the theory. Okay? And in fact, this is tight in the sense that for k, which is the hypercube, nu has to be bigger than n. Okay, so the self-concordance parameter, in general, you cannot hope to take it better than the dimension. Yes, please.
So here you associate with one value.
Yes.
That's the condition number of your
Yes.
barrier, right?
Mm-hmm.
So here this universal barrier, is it when n increases, is this condition number fixed or increases n?
Okay, good. So you're pointing to, I think, one place where I think we can improve, which is, so you know about acceleration. So I told you this, I reminded you of these theorems that with gradient descent, you can get to the optimum in kappa number of steps, where kappa is a condition number. But in fact, there is a better algorithm, which is called Nesterov accelerated method, which gets to the optimum in square root of kappa. So this acceleration phenomenon, which is very important in convex optimization, is not exploited by interpone method. How could you exploit it? You could exploit it if you said, okay, maybe I'm willing to, if you can get me faster, if you can make bigger jumps, but maybe trade off, do longer jumps, but then the condition number is a little bit worse, so that you can exploit this square root effect. Yeah, as far as I know, this is not done. So we did something like that recently in a paper when you want to do optimization over LP balls. We use the acceleration phenomenon exactly in this way. But for the general problem of linear programming, which is like LP regression over with L infinity, we don't know how to do it. But yes, it's a good avenue to look at. Yeah, this is just saying if you stick to what to what I said. Okay, let's see, what do I... Okay, so now what I'm going to tell you is about how to use this for bandits. Okay. Let's just see if there was something else. Maybe I can give you an example of a self-concordant barrier just to give you some feel for it. So just an example. On K, which is, let's say, just a positive orthant. Okay, so this is a cone now. It's not a compact set, but it doesn't matter. You can take phi of x, which is minus the sum of log xi. So this is called the logarithmic barrier, and this is the most important thing for applications. This one is efficient to calculate, and Riemannian geometry is closely related to what we have been working on for bandits. For bandits, we wanted a geometry which we weight points where we have small mass, by that mass. Now, what this is going to do, the Hessian of this will have a 1 over xi squared. Okay. So let's do just the calculation to see that we agree with what I wrote. So what is the gradient of phi of x? So let me just say that this will be useful for us later on. This is also equivalent to saying that grad phi of x applied to h, this is bounded by the Hessian phi of x applied to hh and with a square root. Okay, I will. Again, this is just this is essentially by definition of the dual norm. So you just want that when you test the gradient along any direction, the answer that you find is smaller than square root of nu times the Hessian of phi applied to hh. I like to write it like this because, okay, I already erased the self-concordance, but the self-concordance was that the third order derivative is bounded by the second order derivative with an appropriate thing, right? Self-concordance was that the third order derivative of phi in the direction hhh, this is bounded by 2 times the Hessian of phi of x in the direction hh, and this to the 3/2. Okay, the 1/2 it comes from the norm, and the 3 is for homogeneity in h. Okay, this is self-concordance, this is new self-concordance. So let's do the calculation for this guy. We get this is the gradient is minus the vector with 1 over xi. the Hessian is a matrix with on the diagonal 1 over xi squared. And the third order derivative, it's a tensor, which has on the diagonal, it has only diagonal element, which is 2 minus 2 over xi cubed. Okay, so these are just simple. Now, what is self-concordance? So maybe let me put a 1 over 3 here on the left-hand side. This is a bit nicer. So what is self-concordance? I need to test this guy, against HHH, which is just, again, the tensor is diagonal. So the answer that I find is the sum of 2 over xi cube. And I want this to the 1/3. And I realize that there's a small mistake in my 2, but okay. And what do I want? I want this to be smaller than 2 times the Hessian, which is the sum of hi squared applied over xi squared. And this to the 1/2. And I forgot hi cube here. And wait, why is my 2 wrong? It's 2 to the 1/3? Okay. Let's say it's 2 to the 1/3. Yeah. So if it's 2 to the 1/3, we remove the 2. Okay, but this is just, the L3 norm of this vector, and this is the L2 norm. Okay? And you know that the LP norm is decreasing when P is increasing. Okay, so the L3 norm is smaller than the L2 norm. Okay, just the L infinity is the smallest if you are not renormalizing. So L3 norm is smaller than L2 norm, so self-concordance is just true. Now let's see new self-concordance. New self-concordance is just going to be Cauchy-Schwarz. New self-concordance. So let's see, what do I want to say? Okay, I just erased it, of course. I want to say that the gradient applied to H, so the gradient is a sum of hi over xi. Okay, this in absolute value. I want to say it's smaller than square root of nu times the Hessian of this thing, which is a sum of hi squared over xi squared. Okay, you recognize you can just do Cauchy-Schwarz, and what you will get is nu is n. Okay, so this is Cauchy-Schwarz, implies nu equals n. So we see that this barrier, this logarithmic barrier, is n self-concordant. And we see that the geometry that it defines, it's related somehow to the geometry of the entropy, but it's different. It's more aggressive. The local norm is even smaller. The fact that the local norm is even smaller will lead to some suboptimality for bandits. So let's see that. How are we going to use this for bandits? So now I'm going to tell you about this beautiful paper by Abernethy-Hazan-Rakhlin. So this is 6. Okay, so again, the issue of multiplicative ways, just why are we doing all of this, was that with the bandit estimator, which is this one-point linear regression, you get non-negative entries. So the entropy is not automatically well-conditioned. To go around this, it makes sense to try to look at Mero Descent with self-concordant barriers so that you get, again, the well-conditioning for free, provided that you do small step. So that's what those guys are doing. So Mero Descent with regularizer being a new self-concordant barrier. So let's do the variance calculation when you do just in general Mero descent with those things. So variance calculation. But before that, I need to say something. Yes. So when I say variance calculation, you need to be a little bit careful because now the sampling scheme is going to matter. Okay, so what is a sampling scheme? And what do I mean by sampling scheme? I mean that when you are at a point, here, how do I explode it into, different points? So what those guys are proposing is a following really nice sampling scheme. But do I need to tell you this? That's my question. Let me just think for a minute. Okay, yes. So, sorry. Let me just tell you, before the sampling scheme, let's do the variance calculation just in general. Okay, so we are interested in the expectation of the norm of L tilde t at xt dual squared. This is what we want, which is, and remember that L tilde t, this is sigma t inverse. And now I'm just going to change things a little bit to simplify my life. I'm going to write AT minus XT times AT transpose LT. Okay, notice that this is still unbiased, where sigma t is now the expectation of AT minus XT, AT minus XT transpose. Okay, it's still unbiased. The only thing that I'm missing is this minus xt, but it doesn't matter because it's zero mean. Yeah, I should have done this calculation actually before telling you about interpoint method. That would have been nicer, but okay. Okay, so what is this? So this is the expectation of L tilde t transpose the Hessian of phi at xt inverse applied to L tilde t. Okay, again, I'm going to ignore this. I'm going to assume that this is bounded by 1. This is my normalization right now, that this is bounded by 1. So I get that this is smaller than the expectation of sigma t inverse AT minus xt transpose applied to the Hessian of phi at xt times sigma t inverse applied to AT minus xt. Now, again, same trick as before. I'm going to use that this is a trace. Okay, this thing, it's a real number, it's a trace. So what I can do, and notice that here I get AT minus xt transpose sigma t inverse. So I can put AT minus xt on the other side. And when I take the expectation, AT minus xt times AT minus xt transpose is going to be sigma t. So it will cancel with this sigma t inverse. So it's just one line that this is equal to the expectation of the trace. And what I'm left with is sigma t inverse from here times the Hessian of phi at xt. I apologize for not doing this calculation before. It's a key motivation for looking at barriers. Okay, so now we have this. This is a variance calculation. When you run Mero Descent with this estimator. So now what's happening? What is sigma t? So no matter what you do, at some point, maybe you're going to get towards the corner. Because, in the game, you're starting to identify that this is really the best point. This is the point that you want to play. Now, when you get close to the corner, you have to play a distribution which has this guy as its mean. But there is less and less space. If you want to have zero mean, you will have to make small movement in this direction. There's just no way around it. meaning that there is just no way around the fact that when you get to a corner, sigma t inverse is blowing up. Okay, so when xt tends to the boundary of k, sigma t inverse is blowing up to infinity. At least in some direction, it has to blow up to infinity. Okay, and in fact, if it's really a corner like that, it's in all directions. So if this guy blows up, sorry, and there is a -1 here. If this guy blows up, the only way to have a small variance is if the Hessian inverse shrinks to 0. So this means we need the Hessian inverse to go to 0. Okay, or equivalently, we need that the Hessian of phi is blowing up to infinity as you go to the boundary. Okay, this is just necessary for linear bandit optimization, bandit linear optimization. You need to use a regularizer whose Hessian blows up on the boundary. Otherwise, you just cannot beat the blow up of the variance as you get towards the corner. This is the same phenomenon as with the entropy on the simplex, the fact that when you get towards the corner, you know, the Hessian of the entropy is 1 over xi. So this blows up to infinity. And this blow up is exactly what you needed to cancel the variance. So in the linear case, you see that what you want is the Hessian to blow up. And what you want is really that it blows up in a way that cancels the covariance. So what would be a nice inequality to shoot for? So would be great if the Hessian of phi at xt, at x, was equal to the inverse covariance at x. What do I mean by the, and now you see that the sampling becomes important. Now you see that the way I sample from this point, it's going to give me a certain covariance, and I want the geometry of this sampling to match the geometry of my barrier. If I did have this, then this thing, you know, the Hessian inverse would be sigma, and then this would be, again, sigma times sigma, sigma inverse times sigma, and you would get n, which is exactly the calculation that we had in multiplicative weights. But now we can hope to make it formal if phi is well conditioned, which it will be for these self-concordant barriers. Okay, so this I call a sampling scheme. It's a mapping from K to measures on K. This is a sampling scheme. And now we really need to worry about what is the sampling scheme. And so now in bandit linear optimization, when you run Mero Descent, you're not only choosing a regularizer, but you're also choosing a sampling scheme. And what you're trying to do is you're trying to match the geometry of the sampling scheme with the geometry of the barrier. And the entropic barrier, which I think I will tell you after lunch, is exactly a construction that gives you this. Okay? But for now, I'm going to tell you something weaker that those guys did, Abernethy-Hazan-Rakhlin, which is something with a discrepancy of 1 over n. Okay, so AHR. So this will be true for the entropic barrier. We're going to do it later. The entropic barrier will satisfy this. It will come equipped with a sampling scheme. And AHR, it will give you this with a factor 1 over n here. Okay, so the Hessian will not be as good, which means here you will get times n. Okay, and this is a little bit worse. Okay, you get this n squared. So before I tell you the sampling scheme of AHR, let me say something about the final regret bound that you can expect. So what is the final regret bound? So final bound is going to be that your regret is bounded by, you know, phi of y minus phi of x1 over eta plus eta t, And then, okay, for the entropic barrier, you will get n. And for the AHR sampling scheme, you will get n times n. Okay? Now I need to tell you about this quantity. And this quantity, it's a lemma that I won't do. It's the same as the one that I proved, that the size of the set, you know, it's bad. I mean, it could be infinite. I mean, it is infinite. If y is on the boundary, phi of y is infinite. But the point is that you can step a little bit away from the boundary, and you just get a log. Okay? So this is bounded by nu log t if y is 1 over t away from the boundary. Okay, so whatever the precise definition of being away from the boundary, if you're very, very close to the boundary, but just at distance 1 over t, it doesn't matter if you're comparing your regret to actually that point or to a point a little bit inside. Okay, so you get nu log t here. So when you optimize, you will get square root of nu times n times t. Okay, so AHR, so this is n square root nu t, that's AHR. And for the entropic barrier, we'll show that nu is n, so that's n square root t for, so this is myself with Ron-Eldan. This was 2008, and this is 2016 or 15. Okay, so this is optimal. This is optimal. And you see that these guys, they get also the optimal thing when the self-concordance can be small. Okay? And this works for any self-concordant barrier, whereas this, you need to use the entropic barrier. Okay? So now let me conclude for this morning with the sampling scheme, finally. AHR sampling scheme. So what you do is the following. You are at this point. Now it turns out that, you know, I showed to you that the function is well conditioned on a certain ball, on a certain ellipse around this point. So we know that there is a certain ellipse contained in this body. In fact, it's the ellipse of radius 1. So this is called the Deakin ellipse. Deakin ellipse at x. This is the set of points of the form x plus h, such that the local norm of h at x is smaller than 1. Okay, and this thing is included in your convex body, this is included in K. This is a lemma. So now what those guys propose to do, they don't phrase it like this, but that's what they do, is to sample for a uniform point in this ball. Okay, so this is the sampling scheme. So sampling, so what we're going to do to simplify, we're going to sample from the sphere. So let's call this E of x, this ellipse. Sampling scheme. Pick a point at random. In the boundary of E. Okay. So what I need to do now is to tell you what is the covariance of this thing. But it should be pretty clear that the covariance is exactly, okay, maybe let me do it. So maybe an equivalent description of this is to say that you pick x plus the inverse Hessian of phi at x to the minus 1/2 times u, where u is a random point in the sphere in Sn minus 1. Okay, so this is a set of points Z in Rn such that the Euclidean norm of Z is 1. Okay, just to pick a point at random from an ellipse, you can pick a point at random from a sphere and just distort the geometry accordingly. Okay? This is what this is doing. You see the local norm of this, you know, you will have, when you take the norm with a Hessian of this, you will have 2 Hessian to the minus 1/2, so this will give you a Hessian to the minus 1 times an Hessian, so they will cancel, and this will be of norm 1. Okay, because the norm of U is 1. Okay, so this is the way to sample it. So now what is the covariance? Sigma of x. This is the expectation of, let's say, A minus x transpose. So this is the expectation of the Hessian of phi of x to the minus 1/2 times U transpose Hessian phi of x to the minus 1/2. Now, what is the covariance of a random point on the sphere? So I think you know that to have a distribution which is isotropic, okay, so that the covariance is the identity, you need to sample not from a sphere of radius 1, but from a sphere of radius square root n. Okay, this is the effect of the dimension. Meaning that the covariance of this one is going to be 1 over n. Okay, so this is equal to 1 to the, there is an expectation. This is equal to the Hessian of phi of x to the minus 1/2 times 1 over n times the identity times the Hessian of phi x to the minus 1/2. Okay, so this is equal to 1 over n times the Hessian of phi of x to the minus 1. Okay, which is what I claimed here. Okay, so we see that the covariance, but just intuitively, it should have been clear from the beginning. I just did the calculation to show that you have this discrepancy of 1 over the dimension. Again, why do we have 1 over the dimension? It's because it's the expectation of square root n u times square root n u transpose. This is equal to the identity. Okay, I need to sample from a sphere of radius square root n so that I get something isotropic. Otherwise, the energy on every entry is 1 over n. Just it should be clear. Okay. So you see, this is a little bit suboptimal. The reason why this is suboptimal is because we are constraining ourselves too much in this. Okay? So the way to fix this constraining is that you can tilt the distribution. So maybe I will just say that and not talk too much about the entropic barrier. Maybe I will conclude the next lecture with the entropic barrier if I have time, and I can just tell you the construction right now because I want to tell you about bandit convex optimization, which was the title of the thing. So the entropic barrier. So it's based, the origin of the idea is exactly this, that, you know, this is not using all the space that you have available. If you want to make the covariance bigger, you should sample further away. But if you want to sample further away here, you should sample with a little bit more probability on the left-hand side. You see, to compensate. You get bigger vectors, but and the price to pay to get bigger vectors is that you have a slightly smaller probability and a slightly larger probability on the left-hand side. So these tiltings of uniform measures are very well known, and they go like this. So let's call it a canonical. So we call it the canonical exponential family of K. So the canonical exponential family of K is like this. It's a set of distribution p theta for theta in Rn. And they are defined by this. So the density of p theta with respect to the Lebesgue measure, this is proportional to e to the theta dot x indicator that x is in K. So you see this exponential factor, so you have the uniform measure, and then you just tilt it a little bit. What do I mean? I mean this. This is the direction theta. So you see, what are the level set of this guy? Okay, it goes like this. Okay, it goes up like this. You know, the more I go in this direction, the bigger is this exponential. And you see, the bigger the magnitude, the steeper it is, the increase. Okay? So you see, when I choose a different direction, I will get tilting, you know, in different ways. So this is the canonical exponential family. And the key fact is that there is a duality between the convex body and those parameters. So for any x in K, in the interior of K, let's say, there exists a unique theta such that the mean of p theta is x. Okay, so for any point here, so there are many, many nice proofs of this. Again, a fun exercise to think about. So for any point here, I can find a theta whose mean is going to be this point. We can already see it for the vertices. You see, for the vertices of the convex body, you can see that I can approach it because, let's say for this one, I can just send theta to infinity in that direction. If I send theta to infinity in that direction, I will get more and more mass towards the corner. So eventually I will get a point mass, you know, at infinity, I will get a point mass there. And that way I can get any vertex of the body, and then there is some convexity argument that tells you that you can get anything inside. And this duality, in fact, is witnessed by a convex function. And if some of you are versed in statistics, you know what is this convex function. It's the log Laplace transform, okay, or the log partition function. And this will be the entropic barrier. So duality witnessed by a convex function. So let's call this theta of x. Okay. Witnessed by a convex function. Meaning like this. So you have x here, and this is Rn, and you have theta. So there will be a convex function whose gradient maps like this, and whose inverse gradient maps like that. And you know, when you have an exponential family, how do you associate to a parameter theta, you know, a function, a real valued function whose derivative becomes a mean? It's a log Laplace transform. So phi star of theta, this is equal to log of the integral of exponential theta dot x dx over x in k. If I take the gradient of this, the gradient of phi star at theta, what do I find? Okay, I differentiate the log, so I get the derivative over the integral. So I get the integral of e theta dot x dx over k. What do I get upstairs? I get the gradient of this, which is theta times this. So it's the integral of theta times e theta dot x dx, which is the mean, x. This is the gradient with respect to theta, which means that this is the mean of p theta. So this function is indeed the one that witnesses this duality between, you know, the parameter of the exponential family and its mean. And now the entropic barrier is just phi. Okay, I defined for you phi star, and now phi, you know, the differential dual of this, is the entropic barrier. So the theorem, which I won't prove, but I will say one more word. The theorem, so myself and Ronen-Eldan, is that phi is 1 plus little o of 1 times n self concordant barrier. Okay, so you even get the tide constant out of this. Okay, it's 1 times n. Doesn't really matter for us, but okay. Okay, so it's a self-concordant barrier. So we can apply the general things that I told you before using Mero Descent with this. But now I need to calculate what is the covariance of my sampling scheme. Okay, and this is why this is very nice. Note that the Hessian of the differential dual at theta, you can easily calculate. So you see when you will take the derivative of this, you will first take the derivative of upstairs, you will get XX transpose, and then minus the derivative of downstairs, you will get the second moment. So it's a calculation to show that this is equal to sigma of theta, which is the expectation of, let's say, x minus the mean of theta, x minus the mean of theta transpose, when x is sampled from p theta. Okay, so the second derivative of the differential dual is the covariance. So in fact, this is the same thing as saying that the Hessian of phi at x inverse, this is equal to the inverse covariance at grad phi star, grad phi of x. You know, theta is grad phi of x, so you get this, which is exactly what we wanted. Okay, so the inverse Hessian is equal to the covariance of the sampling scheme. Of course, I didn't say it, but what is a sampling scheme? You know, Mero Descent tells me to play this point. What I do is that I go to the dual and I play a point at random from this distribution, which is exactly doing the tilting that I was telling you about. And by doing this, you remove this nasty 1 over n factor, and you get something optimal. Okay. And what I like, but this is me, I know that the experts in this community disagree, is that the proof of this, I find it much simpler than previous proofs. But okay, this is using some basic things about log concavity. We will see log concavity appearing again when we do the bandit convex optimization this afternoon. Okay, is there any question before we break on this? Did it make sense? Okay, if not, let's go to lunch.